Imagine peering into the cosmos with a machine so sensitive it could detect the faintest whisper of oxygen in the atmosphere of a distant exoplanet, so subtle, it's like smelling a single drop of water in a hurricane. This is the promise of the ELT spectrograph, a colossal instrument perched on Chile's Atacama Plateau, designed to dissect starlight for traces of life's chemical fingerprints. Before the telescope even points its gaze, scientists are already debating what its data might reveal. Could it sniff out methane and oxygen in a world's sky, hinting at microbial life? Or perhaps detect the telltale sign of chlorophyll in a planet's clouds, suggesting forests or algae thriving in the dark? These aren't just hypotheticals, they're the kind of questions that could redefine our place in the universe. And yet, the ELT spectrograph isn't just about discovery, it's about rewriting the rules of what we think life could look like, light years away. Before any major telescope commissioning, there are dozens of papers that attempt to define what we can expect from it. We're starting to see some come through for the Extremely Large Telescope, ELT, which hopefully will get a more imaginative name when the 39M, 128-foot, behemoth is officially commissioned in Chile in the 2030s. This part of our deep dive into ELT spectrograph could sniff out biosignatures on other worlds focuses on, explain plainly what was actually discovered/announced. Lead with the single most important fact, then fill in the necessary detail a curious newcomer needs to understand it. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The search for life beyond Earth has always been a tantalizing mystery, one that has driven humanity's curiosity for centuries. But in recent decades, this search has transformed from speculation into a rigorous scientific endeavor. At the heart of this effort lies a revolutionary tool, the spectrograph. Spectrographs have long been the backbone of astronomical research, allowing scientists to dissect the light from distant stars and planets to uncover their chemical fingerprints. Now, with the advent of the Extremely Large Telescope, ELT, these instruments are poised to take their capabilities to an unprecedented level. The ELT spectrograph, a marvel of engineering and precision, is designed to detect the faintest traces of gases in the atmospheres of exoplanets, potentially revealing the presence of biosignatures, the chemical markers of life itself. But how did scientists arrive at this breakthrough? How did they design an instrument capable of such a feat? And what does this mean for the future of astrobiology? Let's trace the journey from concept to reality, exploring the instruments, methods, and collaborative efforts that make this possible. The ELT, a telescope of staggering scale, stands as a testament to human ingenuity. With a primary mirror spanning 39 meters, equivalent to the length of a football field, this telescope will be the largest ever built. Its construction, set to begin in the 2020s and culminate in commissioning by the 2030s, is a monumental undertaking. Yet, even before its first light, scientists have been working tirelessly to define the telescope's potential. Dozens of research papers have already emerged, outlining what the ELT could achieve. These studies are not just theoretical exercises, they are blueprints for discovery, guiding the development of instruments like the spectrograph that will make the ELT's mission possible. Among these instruments, the spectrograph stands out as a critical component, its design and capabilities meticulously refined to meet the demands of exoplanet characterization. Spectrographs work by splitting light into its component wavelengths, creating a spectrum that reveals the chemical composition of an object. For exoplanets, this process is far more complex. Most exoplanets are too dim to be seen directly, so scientists must rely on indirect methods. One such method is transit spectroscopy, which involves observing the dimming of a star as a planet passes in front of it. During this transit, a small fraction of the starlight passes through the planet's atmosphere, carrying with it the chemical signatures of gases trapped there. By analyzing the subtle changes in the starlight spectrum, scientists can infer the presence of molecules like oxygen, methane, or water vapor, substances that, in certain combinations, could indicate biological activity. But detecting these gases is no simple task. The light from an exoplanet's atmosphere is incredibly faint, often buried in the overwhelming brightness of its host star. To extract meaningful data, the spectrograph must be capable of resolving minute differences in wavelength with extraordinary precision. This requires not only advanced optical technology but also sophisticated data analysis techniques. The ELT spectrograph is designed to overcome these challenges, leveraging its massive mirror to gather more light than any previous telescope. This increased light collection allows for a higher signal-to-noise ratio, making it possible to detect even the faintest spectral lines. However, the design of the spectrograph itself is equally critical. It must be optimized to handle the extreme conditions of space observation, where atmospheric interference and instrumental noise can easily overwhelm the signal. The development of the ELT spectrograph has been a collaborative effort spanning multiple disciplines and institutions. Scientists, engineers, and instrument designers have worked in tandem to ensure that the spectrograph meets the stringent requirements of exoplanet research. One of the key challenges has been the need for high spectral resolution, which allows for the differentiation of closely spaced wavelengths. This is essential for identifying specific molecules, as many gases absorb light at very similar wavelengths. To achieve this, the spectrograph incorporates advanced diffraction gratings and high-precision detectors, enabling it to capture the faintest spectral features. Additionally, the instrument must be capable of operating over a wide range of wavelengths, from the visible spectrum to the infrared, where many biosignatures are expected to be found. The timeline leading to the ELT's commissioning has been marked by a series of milestones, each bringing scientists closer to their ultimate goal. In the early stages, researchers focused on theoretical modeling, simulating how the ELT spectrograph would perform under various conditions. These simulations helped refine the design, ensuring that the instrument could handle the complexities of exoplanet atmospheres. As the project progressed, prototype components were developed and tested, with each iteration bringing improvements in sensitivity, resolution, and reliability. By the time construction began, the spectrograph's design had been finalized, and the focus shifted to integrating it into the telescope's overall system. This integration required careful coordination, as the spectrograph must work seamlessly with other instruments, such as the adaptive optics system that corrects for atmospheric distortions. The role of the ELT spectrograph in the broader context of exoplanet research cannot be overstated. While other telescopes, such as the James Webb Space Telescope, JWST, have already begun to probe the atmospheres of exoplanets, the ELT spectrograph offers a unique advantage. The JWST operates in space, free from the interference of Earth's atmosphere, but its size and design limit the number of exoplanets it can study in detail. The ELT, on the other hand, will be Earth-based but will benefit from its immense size, allowing it to observe a larger number of targets with greater precision. The spectrograph's ability to analyze the light from these distant worlds will be crucial in identifying potential biosignatures, providing a more comprehensive view of the diversity of exoplanetary atmospheres. The process of detecting biosignatures is not without its challenges. Even with the ELT's advanced capabilities, distinguishing between biological and non-biological sources of gases remains a complex task. For example, oxygen can be produced by both biological and non-biological processes, such as photolysis of water. Similarly, methane can be generated by geological activity or microbial life. To address these uncertainties, scientists must employ a multifaceted approach, combining spectroscopic data with other observations, such as the planet's temperature, atmospheric pressure, and orbital characteristics. The ELT spectrograph will play a vital role in this process, providing high-resolution data that can help differentiate between possible explanations for the observed signals. The journey to develop the ELT spectrograph has been a testament to the power of collaboration and innovation. From the earliest theoretical models to the final integration into the telescope, each step has required ingenuity and perseverance. The scientists involved in this project have not only pushed the boundaries of what is technologically possible but have also laid the groundwork for future discoveries. As the ELT moves closer to its commissioning date, the anticipation grows for the first light it will capture, a moment that could redefine our understanding of life in the universe. The spectrograph, with its ability to sniff out biosignatures, is more than just an instrument. It is a bridge between the known and the unknown, a tool that may one day reveal whether we are truly alone in the cosmos. Before any major telescope commissioning, there are dozens of papers that attempt to define what we can expect from it. We're starting to see some come through for the Extremely Large Telescope, ELT, which hopefully will get a more imaginative name when the 39M, 128-foot, behemoth is officially commissioned in Chile in the 2030s. This part of our deep dive into ELT spectrograph could sniff out biosignatures on other worlds focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For millennia, humanity has gazed at the stars, wondering if we are alone. The quest to find life beyond Earth has shaped our understanding of the cosmos, evolving from philosophical musings to rigorous scientific exploration. In the 19th century, astronomers like William Herschel began to grasp the vastness of the universe, but the tools to probe distant worlds were rudimentary. It wasn't until the 20th century that technology advanced enough to begin answering the question, are we truly alone? The search for extraterrestrial life has always been a blend of imagination and science, but it was the development of spectroscopy, a technique that analyzes light to uncover the chemical composition of distant objects, that laid the foundation for modern astrobiology. Spectroscopy allowed scientists to detect the presence of elements and molecules in stars, nebulae, and even planets, revealing the building blocks of life itself. This method, once a niche tool, became central to the search for biosignatures, chemical indicators that suggest the presence of life. The journey from early spectroscopic observations to the cutting-edge spectrograph of the Extremely Large Telescope, ELT, is a story of incremental breakthroughs, each building on the last. It began with the discovery of exoplanets in the 1990s, a revelation that transformed our view of the universe. Before then, the idea of planets orbiting other stars was largely theoretical. The first confirmed exoplanet, 51 Pegasi b, was found in 1995, and its discovery ignited a new era of planetary science. Suddenly, the possibility of life beyond our solar system was no longer a distant dream but a tangible scientific pursuit. Yet, even with the ability to detect planets, the challenge remained: how to determine if any of them harbored life. This is where spectroscopy took center stage. By analyzing the light that passes through a planet's atmosphere, scientists could identify the presence of gases like oxygen, methane, or water vapor, chemical signatures that might indicate biological activity. However, the technology to perform such analyses was limited. Early telescopes lacked the resolution and sensitivity needed to study exoplanet atmospheres in detail. The Hubble Space Telescope, launched in 1990, provided a glimpse into this realm, but its capabilities were constrained by its size and the faint light of distant worlds. It was the James Webb Space Telescope, JWST, launched in 2021, that marked a significant leap forward. With its advanced infrared instruments, JWST has enabled scientists to peer into the atmospheres of exoplanets, detecting molecules that could be linked to life. Yet, even JWST's achievements are just the beginning. The ELT, with its 39-meter primary mirror, represents the next frontier in this quest. Before any major telescope is commissioned, scientists and engineers work tirelessly to define its potential. Dozens of papers have already emerged outlining what the ELT could achieve, from studying the formation of galaxies to detecting biosignatures on potentially habitable exoplanets. The ELT spectrograph, a critical component of this mission, is designed to analyze light with unprecedented precision. This instrument could sniff out the faint chemical signatures of life on other worlds, a capability that has long been the dream of astrobiologists. But to appreciate the significance of the ELT spectrograph, we must look back at the milestones that brought us here. The search for life beyond Earth has always been intertwined with the study of our own planet. The discovery of microorganisms in extreme environments on Earth, such as hydrothermal vents and subglacial lakes, expanded our understanding of where life can exist. These findings suggested that life might thrive in similar conditions on other planets, such as Mars or the moons of Jupiter and Saturn. The Viking landers of the 1970s attempted to detect life on Mars, but their results were inconclusive. It wasn't until the 1990s, with the advent of exoplanet detection, that the focus shifted to searching for habitable worlds. The discovery of the first exoplanet orbiting a sun-like star in 1995 sparked a wave of new research. Scientists began to ask not just if planets exist, but whether they could support life. This led to the development of the concept of the habitable zone, the region around a star where temperatures are just right for liquid water to exist. The search for planets in this zone became a priority, as water is a key ingredient for life as we know it. However, detecting life requires more than just finding a planet in the habitable zone. It demands the ability to analyze the atmosphere of such a world for biosignatures. This is where spectroscopy became indispensable. By studying the light that passes through a planet's atmosphere, scientists can identify the presence of gases that might indicate biological activity. For example, oxygen is a strong biosignature because it is continuously consumed by life on Earth and would need constant replenishment. Similarly, methane, produced by both biological and geological processes, could be a clue. However, distinguishing between biological and non-biological sources remains a challenge. The ELT spectrograph is designed to overcome these limitations by providing higher resolution and sensitivity. It will allow scientists to study the atmospheres of exoplanets in greater detail, potentially identifying complex molecules that are more indicative of life. The development of such technology has been a gradual process, driven by decades of scientific inquiry and technological innovation. The early days of spectroscopy were marked by the work of pioneers like Joseph von Fraunhofer, who discovered dark lines in the spectrum of sunlight in the 1810s. These lines, now known as Fraunhofer lines, correspond to specific wavelengths absorbed by elements in the atmosphere. This discovery laid the groundwork for understanding the composition of distant objects. In the 20th century, spectroscopy became a cornerstone of astrophysics, enabling the study of stars, galaxies, and planetary systems. The ability to detect elements and molecules in space transformed our understanding of the universe, revealing the chemical processes that govern celestial bodies. As the field of astrobiology emerged in the late 20th century, spectroscopy became a vital tool for the search for life. The challenge, however, was always the same: how to apply this technique to exoplanets, which are incredibly faint and distant. The first attempts to study exoplanet atmospheres in the 1990s and 2000s were limited by the technology of the time. Instruments like the Hubble Space Telescope could detect some atmospheric features, but their resolution was insufficient for detailed analysis. It wasn't until the development of more advanced telescopes, such as the Keck Observatory in Hawaii and the Very Large Telescope, VLT, in Chile, that scientists began to make progress. These ground-based telescopes, equipped with adaptive optics technology, could correct for atmospheric distortions and provide clearer images of distant planets. The VLT, in particular, played a crucial role in the study of exoplanet atmospheres, demonstrating the feasibility of spectroscopic analysis. However, the next leap in capability came with the James Webb Space Telescope, which operates above the Earth's atmosphere, eliminating the interference of atmospheric turbulence. JWST's infrared instruments have already provided groundbreaking insights, such as the detection of water vapor in the atmosphere of exoplanets like K2-18b. These discoveries have set the stage for the ELT, which will take this research to new heights. The ELT spectrograph is not just an extension of previous technology, it represents a paradigm shift in our ability to study distant worlds. With its unprecedented light-gathering power, the ELT will be able to analyze the atmospheres of exoplanets that are currently beyond the reach of even the most advanced telescopes. This means that scientists will be able to study planets in the habitable zones of distant stars, searching for the chemical signatures of life. The potential applications of this technology are vast. Beyond the search for biosignatures, the ELT spectrograph could help us understand the formation and evolution of planetary systems, study the atmospheres of gas giants, and even detect the presence of complex organic molecules. These findings would not only advance our understanding of the universe but also provide insights into the origins of life itself. The journey from early spectroscopic observations to the ELT spectrograph is a testament to human ingenuity and perseverance. Each breakthrough in technology has brought us closer to answering the question of whether we are alone in the cosmos. The ELT, with its groundbreaking spectrograph, is poised to play a pivotal role in this quest. As we look to the future, the possibilities are as vast as the universe itself. The search for life beyond Earth is no longer a distant dream but an active scientific endeavor, driven by the relentless pursuit of knowledge. The ELT spectrograph, with its ability to sniff out biosignatures, represents the next step in this journey, a step that could redefine our understanding of life in the universe. The extremely large telescope, with its groundbreaking spectrograph, stands at the forefront of humanity's quest to detect life beyond Earth. Yet, even as scientists eagerly anticipate its capabilities, a web of open questions and scientific debates continues to shape the field. The promise of biosignatures, chemical markers that could hint at life, remains tantalizing, but the path to confirming their presence is fraught with complexity. What exactly constitutes a biosignature? How can we distinguish between biological and non-biological processes? And what happens when the data we gather doesn't align with our expectations? These are not just technical hurdles, they are profound mysteries that challenge our understanding of life itself. The ELT spectrograph, for all its advanced design, is not a magic wand. It is a tool that requires careful calibration, rigorous interpretation, and a willingness to confront the unknown. As scientists prepare for its commissioning, they are also grappling with the limitations of current technology and the vastness of the unknown. For instance, while the spectrograph's ability to analyze the atmospheres of exoplanets is revolutionary, it cannot yet resolve the question of whether a gas like oxygen or methane, commonly associated with life, might arise from non-biological processes. The same gas could be produced by volcanic activity, hydrothermal vents, or even the breakdown of minerals in a planet's atmosphere. This ambiguity means that any detection of such a gas must be accompanied by a thorough analysis of other atmospheric components. For example, the presence of ozone, which is a byproduct of oxygen-rich atmospheres, might provide additional context. However, ozone itself could be generated by non-biological mechanisms, such as ultraviolet radiation interacting with other molecules. The challenge, then, is not just in detecting these gases but in interpreting their significance. Scientists must consider the full suite of atmospheric data, including the presence of other gases like water vapor, carbon dioxide, or even noble gases, which might offer clues about a planet's geological or chemical history. This interplay of factors means that the search for biosignatures is not a simple yes or no question but a nuanced puzzle requiring careful assembly. Another layer of complexity arises from the sheer scale of the task. The ELT spectrograph will analyze exoplanets that are light years away, their atmospheres compressed into a tiny fraction of the data collected. Even with the telescope's immense light-gathering power, the signal from these distant worlds will be faint, requiring sophisticated algorithms to extract meaningful information. This is where the debate over data interpretation comes into play. How do scientists ensure that their models of planetary atmospheres are accurate enough to avoid false positives? For example, a planet with a thick atmosphere rich in methane might be interpreted as a sign of microbial life, but methane can also result from geological activity or even the breakdown of organic matter in a planet's crust. The same applies to oxygen, which, while often associated with photosynthesis, could also be produced by chemical reactions involving water in minerals. These possibilities mean that any detection of a biosignature must be corroborated by additional evidence. This is where the scientific community's collaborative efforts become crucial. Researchers are working to develop multi-pronged approaches, combining data from the ELT with observations from other telescopes, such as the James Webb Space Telescope, to cross-check findings. For instance, the JWST's ability to analyze the chemical composition of exoplanet atmospheres could complement the ELT's spectrographic data, offering a more comprehensive picture. However, even with these tools, the search is not without its uncertainties. One of the most pressing questions is whether life on other worlds would even resemble what we know on Earth. Our current understanding of biology is based on carbon-based life forms that rely on liquid water and specific chemical processes. But what if life elsewhere is fundamentally different? For example, some scientists speculate that life might exist in environments with alternative solvents, such as ammonia or methane, or thrive in extreme conditions like high temperatures or radiation exposure. If such life exists, it might produce biosignatures that are entirely unfamiliar to us. This possibility means that our current models of what constitutes a biosignature could be incomplete or even misleading. The ELT spectrograph, while powerful, may not be equipped to detect these unconventional signatures, highlighting the need for continued innovation in both technology and theory. Another unresolved issue is the potential for false negatives, cases where life exists on a planet, but its biosignatures go undetected. This could happen if the life forms are too small, too sparse, or if their metabolic processes do not produce detectable gases. For example, microbial life might exist in environments where the atmospheric pressure is too low to allow for the accumulation of gases like oxygen or methane. Alternatively, life could be so deeply embedded in a planet's geology that its chemical traces are obscured by other processes. These scenarios underscore the importance of developing a broader range of detection methods. Scientists are exploring ways to identify biosignatures that do not rely solely on atmospheric gases. For instance, the presence of certain isotopes in a planet's atmosphere or surface materials could indicate biological activity. Isotopic ratios, which reflect the processes that create and destroy elements, might provide clues about the presence of life. However, interpreting these ratios requires a deep understanding of both geological and biological processes, making it a challenging area of research. Moreover, the ELT spectrograph must contend with the limitations of its own design. While it is optimized for high-resolution spectroscopy, it may still struggle with certain aspects of atmospheric analysis. For example, the spectrograph's ability to detect faint signals could be compromised by factors such as atmospheric turbulence or instrumental noise. These technical challenges mean that even with the ELT's capabilities, there will be cases where the data is insufficient to draw definitive conclusions. This is why the scientific community is emphasizing the need for careful calibration and validation of the telescope's instruments. Researchers are also working to refine the models that predict how different atmospheric conditions might appear in the data. These models are essential for interpreting the spectrographic results, as they help scientists distinguish between natural variations and potential biosignatures. However, these models are inherently limited by our current understanding of planetary science. For instance, the way light interacts with a planet's atmosphere can be influenced by factors such as cloud cover, surface albedo, and even the presence of aerosols. These variables add layers of complexity to the analysis, requiring scientists to account for a wide range of possibilities. In this context, the ELT spectrograph represents not just a technological achievement but a critical step in a broader scientific endeavor. Its data will be part of a larger puzzle, one that requires collaboration across disciplines and the willingness to question assumptions. The search for biosignatures is not just about finding life, it is about redefining what we consider possible. As scientists prepare for the ELT's commissioning, they are also engaging in a continuous dialogue about the nature of life and the methods we use to detect it. This debate is as much about the unknown as it is about the known. It is a testament to the human spirit of inquiry, driven by the desire to understand our place in the universe. The ELT spectrograph, with its potential to sniff out biosignatures, is a powerful tool in this quest. Yet, it is also a reminder that the search for life beyond Earth is as much about the questions we ask as the answers we seek. As the telescope moves closer to its operational debut, the scientific community remains focused on refining its methods, addressing its limitations, and embracing the uncertainties that come with exploring the vast, uncharted territories of the cosmos. As the extremely large telescope, ELT, inches closer to its 2030s commissioning date in Chile, the scientific community is already looking ahead to the next chapter in the search for life beyond Earth. The ELT spectrograph, a cutting-edge instrument designed to dissect the light from distant exoplanets, represents a leap forward in our ability to detect biosignatures, chemical markers that could indicate the presence of life. But even as the ELT prepares to take its first observations, the field of astrobiology is bracing for a wave of new missions, instruments, and observational techniques that will build on its capabilities, challenge existing assumptions, and expand the boundaries of what we think is possible. These efforts are not just about refining our tools, they are about redefining the very questions we ask about the universe and our place within it. The ELT spectrograph is a marvel of engineering, capable of analyzing the faint light from exoplanet atmospheres with unprecedented precision. Its ability to detect subtle variations in light, such as the absorption of specific wavelengths caused by gases like oxygen, methane, or water vapor, could reveal the fingerprints of life. However, the ELT is just one piece of a much larger puzzle. Already, scientists are planning follow-up missions that will complement its work, addressing its limitations and pushing the search for biosignatures into new frontiers. For instance, the James Webb Space Telescope, JWST, which has already begun its mission, has provided critical insights into exoplanet atmospheres. While JWST's instruments are highly sensitive, they are limited by their design to observing in the infrared range. The ELT, with its ground-based spectrograph, can access a broader spectrum of light, making it uniquely suited to detect a wider array of biosignatures. Yet, even with these advancements, the search for life requires more than a single instrument. The next generation of telescopes and observatories will need to work in concert with the ELT to paint a more complete picture of the cosmos. One of the most anticipated projects in this regard is the LUVOIR, Large UV Optical Infrared Surveyor, a proposed space-based telescope that could revolutionize our ability to study exoplanets. LUVOIR, if funded, would be a massive telescope with a mirror up to 15 meters in diameter, capable of imaging exoplanets directly and analyzing their atmospheres with remarkable clarity. Unlike the ELT, which relies on indirect methods to study exoplanet atmospheres, LUVOIR could capture direct images of planets orbiting other stars, allowing scientists to observe their surfaces, clouds, and atmospheric dynamics in real time. This would be a game changer, as direct imaging would enable the detection of biosignatures that are currently beyond our reach. For example, LUVOIR could potentially identify complex organic molecules or even signs of biological activity on the surface of a planet, such as vegetation or water bodies. While LUVOIR is still in the planning stages, its potential to complement the ELT's spectrographic capabilities is already being explored in scientific collaborations. The data gathered by the ELT could help prioritize targets for LUVOIR, ensuring that the most promising exoplanets are studied with the highest resolution instruments available. Another key player in the future of biosignature detection is the Habitable Exoplanet Observatory, HABEX, a NASA-led mission that aims to search for life on planets in the habitable zones of their stars. HABEX would be a large space telescope designed to study exoplanet atmospheres using a combination of spectroscopy and direct imaging. One of its unique features is its ability to use a coronagraph, a device that blocks the light from a star to reveal the faint light of an orbiting planet. This would allow HABEX to study the atmospheres of planets that are too dim to be observed with current technology. The HABEX mission is still in the conceptual phase, but its potential to work alongside the ELT is already being considered. For example, the ELT could identify exoplanets with intriguing atmospheric compositions, while HABEX could then conduct more detailed analyses to confirm whether those compositions are indicative of life. This kind of collaboration between ground-based and space-based observatories represents a new era in planetary science, where the strengths of each platform are leveraged to achieve a common goal. Beyond these major missions, there are also smaller but equally important projects that will contribute to the search for biosignatures. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, is one such example. While its primary mission is to map dark energy and study the structure of the universe, the Roman telescope will also play a role in exoplanet research. It is equipped with a microlensing camera that can detect planets in distant star systems, many of which may be too far for the ELT to study. By identifying these planets, the Roman telescope will provide the ELT with a list of potential targets, expanding the scope of its observations. Additionally, the Roman telescope's ability to detect exoplanets through microlensing could help scientists identify planets that are otherwise invisible to traditional methods, such as those orbiting dim red dwarf stars. These planets, which are often considered prime candidates for hosting life, could be studied in greater detail by the ELT in other future missions. However, the search for biosignatures is not without its challenges. One of the most significant hurdles is the risk of false positives, chemical markers that may appear to indicate life but are actually the result of non-biological processes. For example, methane in an exoplanet's atmosphere could be produced by geological activity rather than biological processes. Similarly, oxygen, which is a common biosignature, can also be generated by abiotic reactions involving water and minerals. To address these challenges, future missions will need to employ a combination of techniques to distinguish between biological and non-biological sources. This could involve using multiple spectroscopic methods, analyzing the chemical complexity of detected molecules, or even searching for multiple biosignatures simultaneously. For instance, the presence of both oxygen and methane in an exoplanet's atmosphere would be a stronger indicator of life, as these gases tend to react with each other and would require a continuous source to maintain their concentrations. The ELT and its successors will need to incorporate such multi-pronged approaches to ensure that any detected biosignatures are as robust as possible. Another critical aspect of the future search for life is the development of new technologies that will enhance our ability to detect biosignatures. Advances in spectroscopy, for example, are already underway, with researchers working on instruments that can capture even fainter signals from distant worlds. These instruments could be deployed on the ELT or integrated into future missions like LUVOIR or HABEX. Additionally, the use of machine learning and artificial intelligence is becoming increasingly important in analyzing the vast amounts of data generated by these telescopes. By training algorithms to recognize patterns in atmospheric spectra, scientists can more efficiently identify potential biosignatures and reduce the likelihood of false positives. These technological innovations will not only improve the accuracy of biosignature detection but also accelerate the pace of discovery, allowing researchers to process data more quickly and focus on the most promising candidates. The ELT spectrograph is also part of a broader network of ground-based observatories that will play a vital role in the search for life. While the ELT is the largest of these, other telescopes, such as the upcoming 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will complement its work by providing additional data points. These telescopes, which are also planned for construction in the 2030s, will have similar capabilities to the ELT but may be located in different regions of the world, allowing for observations that take advantage of different atmospheric conditions. For example, the TMT, which will be built in Hawaii, will have access to clearer skies due to its location, while the GMT, planned for Chile, will share the same site as the ELT. Together, these telescopes will form a powerful array of instruments capable of studying exoplanet atmospheres with unprecedented detail. The synergy between these observatories will be crucial, as the data they collect will need to be combined and cross-referenced to build a comprehensive understanding of the atmospheres of distant worlds. As we look to the future, it's also important to consider the broader implications of these missions. The search for biosignatures is not just about finding life, it's about understanding the conditions that make life possible and how common or rare such conditions might be. The ELT and its successors will provide valuable insights into the diversity of exoplanet atmospheres, helping scientists determine whether our solar system is unique or if life is a common phenomenon in the universe. For example, if the ELT detects a biosignature on an exoplanet that is similar to Earth, it could suggest that life is more widespread than previously thought. Conversely, if no biosignatures are found, it might indicate that the conditions necessary for life are extremely rare, prompting a re-evaluation of our assumptions about habitability. These findings will have profound implications for our understanding of biology, chemistry, and the potential for life beyond Earth. In addition to the scientific discoveries they may enable, these missions will also have a lasting impact on technology, engineering, and international collaboration. The development of the ELT and other large telescopes requires the expertise of thousands of scientists, engineers, and technicians from around the world. This global effort reflects the shared human curiosity about our place in the universe and the desire to explore the unknown. As these telescopes come online, they will not only advance our knowledge of the cosmos but also inspire new generations of scientists and engineers to pursue careers in space exploration and planetary science. The collaborative nature of these projects underscores the idea that the search for life is a collective endeavor, one that transcends national boundaries and cultural divides. Looking ahead, the next few decades will be a period of unprecedented discovery in the search for life beyond Earth. The ELT spectrograph is just the beginning of a new era in astrobiology, one that will be driven by the combined efforts of ground-based and space-based observatories, cutting-edge technology, and international collaboration. As scientists continue to refine their methods and expand their capabilities, the possibility of finding biosignatures on other worlds becomes increasingly tangible. While the journey is still in its early stages, the potential for discovery is immense, and the questions we ask about the universe are only beginning to be answered. The search for life is not just about finding evidence of life, it's about expanding our understanding of what life could be, how it might exist, and what it might mean for our place in the cosmos. As we wrap up this deep dive, 3 key ideas stand out. First, the extremely large telescope spectrograph is more than just a tool, it's a revolutionary instrument designed to peer into the atmospheres of exoplanets and hunt for the chemical fingerprints of life. By analyzing starlight filtered through these distant worlds, it could detect gases like oxygen, methane, or even complex organic molecules that might signal biological activity. Second, the path to this breakthrough isn't just about building a massive telescope. It's about years of collaborative science, with researchers around the world already debating what the ELT could achieve before it even turns its eye to the cosmos. These papers aren't just technical specs, they're blueprints for how we'll redefine our search for life. And third, this isn't just about finding alien microbes or plants. The ELT spectrograph is part of a broader mission to answer one of humanity's oldest questions: are we alone? By combining cutting-edge technology with decades of planetary science, this telescope could bridge the gap between our solar system and the vast, uncharted realms of the galaxy. But let's not forget, this is just the beginning. The ELT spectrograph is a marvel of engineering, but it's also a reminder of how far we've come in understanding the universe. From the first telescopes that mapped the stars to today's instruments that can analyze alien atmospheres, each step has been driven by curiosity and the relentless pursuit of knowledge. So, what does this mean for the future? It means we're standing on the edge of a new era in astronomy. The ELT spectrograph isn't just a machine, it's a window into the unknown, a chance to glimpse the possibilities of life beyond Earth. And while the 2030s are the target for its commissioning, the science behind it has already begun. Researchers are refining methods, testing technologies, and imagining the discoveries that await. This is the power of collaboration, of scientists working across disciplines to turn speculation into reality. But the journey doesn't end here. The ELT spectrograph is part of a larger story, one that connects the study of our own planet to the search for life in the cosmos. By understanding Earth's atmosphere, we've built the foundation for interpreting the atmospheres of distant worlds. It's a reminder that the tools we use to explore space are often rooted in the very science that helps us understand our place in it. So, as we look to the future, the ELT spectrograph represents more than just a technical achievement. It's a testament to human ingenuity, a symbol of our drive to explore, and a beacon for the next generation of scientists who will carry this quest forward. If you've enjoyed this deep dive into the science behind the ELT spectrograph and its potential to revolutionize our search for life, hit that subscribe button to join us for daily space and science explorations. And if you have a question, a theory, or a thought about what we might find when this telescope finally begins its work, drop a comment below. The universe is full of mysteries, and together, we're just beginning to uncover them.